Yeah, we started this section on modeling of DC to DC converters, right? As I mentioned last time, two ways to do this: state space and transfer functions. And I introduced, not I introduced, but reviewed the state space. I started by reviewing the state space equations first, and then later we do the transfer function. So for state space equations, basically this is the block diagram of a system represented by state space equation, right? X dot equals to x plus bu and y is equal to cx plus du, right? And again, x would be our state variables. X dot would be the first derivative of our state variables, and u would be our inputs. Y would be our output or outputs, right? And these are all matrix equation, okay? And I went over the first example, setting up the matrix equation. These are already given to you. The equations are already derived for you. And so once you get derivations, once you get the equations, that looks something like this, right? Where you see the first derivative of the state variables on the left side and the state variables and input on the right-hand side, then you can start converting the equations into matrix equation, right? That way we can see the A matrix, the B matrix, right? The C matrix and the D matrix, okay? And I've also mentioned last time that for us, for electrical engineering, for our world, state space, our state variables are typically capacitor voltage and inductor current, right? And I also mentioned last time that the reason why we want to pick voltage across the capacitor, that would be easy for us to derive. It would be convenient, not easy, but convenient for us to derive the state space equations, because then we know that the first derivative of VC will be dVC dt, and that would be obtained from current through the capacitor, right? And likewise, current through the inductor, we picked that one instead of voltage across the inductor, because I know that if I pick IL of t, then the first derivative would be IL dIL dt. And that's going to be part of the equation for voltage across the inductor, right? So you get the first derivative of IL from voltage across inductor. And when assigning a state variable, make sure that it is independent of the other state variables. And so an example would be this first one. It basically means that state variables cannot be linearly dependent from one another, right? Like this one right here, right? L, IL, and VC, they're not dependent on each other. So therefore, I could have two state variables for this circuit, right? One input, and I don't know if I defined the output. Looks like I did not. So one input and two state variables. Input, as you already learned from previous classes, right? That input would be defined from independent source, right? The next example, you can see that I have one input. There's one independent source, which is our voltage source. And we have two capacitors that are in parallel. Because they are in parallel, therefore, VC1 is equal to VC2. In this case, I don't need to assign two state variables, right? Because they would be linearly dependent on each other, right? VC1 equals to VC2. So in this case, just pick one of the two, right? Maybe VC1 to be your state variable or VC2 to be your state variable. Then the other one, you can always get it because it's equal, right? Let's look at the third one right here. Here I have one input. I have 1, 2, 3 energy storages, right? 3 energy storage components, L1, L2, and C1. And you can see clearly that L1 and L2 are in series. So in terms of our state variable, IL1, these currents, IL1 and IL2 are the same current, right? So therefore, they're linearly dependent. And so in that case, I don't need to assign two separate state variables for L1 and L2. I could just pick one, either IL1 or IL2. Okay. So far, so good. All right. How do you determine the size of matrices in state space equations? So this is actually good to check, right? To check what once you derive the equations, state space equations, you get matrices, right? You get matrix A, B, C, and D. One way to check to see if your work is correct is by looking at the size of or the dimensions of these matrices, right? A, for example, right? Matrix A, the size of matrix A should be n by n. Where is it? Right there. N by n. N being the number of state variables. So I forgot to mention. N is the number of state variables. I is the number of inputs. O is the number of outputs. And so matrix A would be n by n. Matrix B would be n by I, right? And matrix C would be O by n. And lastly, matrix D would be O by I. Okay. For example, right here, I have the state space variable equations already set up in the matrix equation. Right, you can see that from here, I know that A must be n by n. Right, let me go back right there. A should be n by n. So knowing this, I know that for a system, let me change it to red. For the system represented by the state space equations, I know from the A matrix that there are n equals to 3, right? There are 3 state variables for this system. So right away I know. And then how many inputs? Well, that's going to be the B matrix, n by I, right? So n is 3, I is 2, right? So you can see, let me write it down. This is 3 by 3. This is 3 by 2. So right away I know from here that we have 3 state variables, right? And I have from the B matrix, that's n by I, right? So this must be 2 inputs, right? So without looking at the actual circuit that formed this state space equation, I already know that the system or the circuit has 3 state variables and 2 inputs. And then how many outputs do we have in the system? That could be from matrix C or matrix D, right? Matrix C would be O by n, right? So O by n, so that's 2 by 3, O by n. So I know that this 2 refers to the number of outputs, 2 outputs. All right. So likewise, if you start from a circuit, right? Let's say, do I have it? Yeah. Let's say you start from a circuit, and from the circuit you determine that there are four state variables, 3 outputs, and 2 inputs. Then once you complete the derivation, once you finish deriving the state space equation, at the end, matrix A that you get should have a dimension of 4 by 4, right? Because there's 4 state variables. Matrix B should be 4 by 2. Matrix C should be 3 by 4, and matrix D should be 3 by 2. That's very important, actually. It's a simple step, but really important to check to see if your work is correct, right? By just looking at the dimensions, right? And once you find out that, hey, my matrix C is actually 4 by 3, then you know that you did something wrong, right? Instead of 3 by 4. And it's a quick check to determine whether or not you did the derivation correctly. All right. Let's or any questions before I move on to examples? Yeah, if not, guidelines on how to form state space equations in electric circuits. Right. So this is strictly electric circuits. So I have this step-by-step procedure on how to form the state space equations. Right. Number 1, determine the number of state variables, keeping in mind the restrictions, recognizing the inputs and the outputs. and then assign each state variable with x1, x2, and so on. Right? Number 3, derive the differential equations involving the state variables using KCL, KVL, Ohm's law, mainly those 3. Right? And then from those obtained in 3, solve for the first derivative of the state variables. Let's see. And then check to see if the right-hand side of the equations obtained in 4 consists only of the terms involving state variables, not its derivative. And inputs. Remember, x dot is equal to ax plus bu, y is equal to cx plus du. So you can see from these state space equations, the right-hand side of the equation must only consist of state variables and inputs. See that? Nothing else. If you see something else, then you have to substitute the equation with something else, so that at the end you get just x and u on the right-hand side of the equations. All right. If step number 5 is confirmed, meaning on the right-hand side you have x and u only, then you're done with the x dot equations. Else you would need to use KVL, KCL, or Ohm's law until step 5 is completed. And then step number 7, derive the equations for the outputs. That's the second equation, right? Outputs, right here. That's after you're done with the x dot. Now you need the output equation, allowing only state variables and inputs on the right-hand side, just like before, just like the x dot equations. Or else you need more substitution using KVL, KCL, or Ohm's law. And number 8, convert step 5 and 7 into matrix equations, i.e. the state space equations, right? And then number 9, check the size of each matrix A, B, C, and D, right? So these are basically step-by-step procedure that I believe would be good to follow, right, when forming state space equation from a circuit. All right. Any questions? Okay. If not, then let's look at this first example. Right. I have this circuit right here. Right. Just from this circuit itself, can you tell me how many input do we have? Somebody? How many input do we have for this circuit? Somebody answer?
Just the one input.
Just the one input. Okay, how many state variables?
2 state variables.
Very good. So we have, just by looking at the circuit, right, and realizing what we discussed earlier, right, about how to pick state variables and inputs, we know right away that U, there's only one, and N, there's two, right? So by knowing this, I know the matrix, the size of the matrix, right? The sizes of the matrix, right? And we have output here, yes. So output is defined to be Y is equal to V out. So there's only one output. So output is only one. Oops, only one, right? So just by knowing this, right, numbers, I already know what to expect, right, from A, B, C, and D. So A should be a 2 by 2, right? And B should be N by I, wasn't it? So a 2 by 1 matrix. C should be, what is it? O by N, if I'm not mistaken. O by N is 2 by 1. And the output matrix D would be O by I believe. So that's 1 by 1. Right. Let's check. For C and D, that's the one I'm sure of. O by N, O by I. Okay, yes. O by N, O by I. Okay. O by N. Oh, I got it wrong, huh? I got it wrong. O by N, O by I. Okay. O by N is 1 by N. There you go, right? O by N, O by I. You all agree with this? Okay. Oops. Let's go back. Okay, state variables. Let's see. I pick x1 to be equal to VC. So therefore, x1 dot is dVC dt, right? X2 would be IL, and therefore x2 dot would be DIL dt, right? And then output is defined to be a voltage across resistor right there. All right. So how do we solve this? How do we derive the state space equations? Remember, x dot is equal to AX plus BU, right? Y is equal to CX plus DU, right? And let's start with x dot equation, right? So I need dVC dt and I need DIL dt. Now, think about it first. If you're looking for the equation for x1 dot, that's dVC dt, right there. Just focus on dVC dt. What law do you apply for the circuit? Is it KCL or KVL? Anybody? So mutual inductance, we started with something. Anybody can answer that? It's just a review from
Maybe KVO? Because it's a DVDT.
for dVC-dt, right? For dVC-dt, we know that the dVC-dt is part of the equation for current through the cap, right? So IC is equal to C dVC-dt, right? That's how we can get the dVC-dt from IC, right? Because it is coming from IC, therefore, the law that we should apply to the circuit to get dVC-dt must be KCL. So yeah, you got it right. Okay. And for DIL dt, now you know where I'm going at, right? Where I'm going with this. With DIL dt, I know that would be coming from BL equals to L DIL dt, right? Right there. And you can see that comes from voltage across the inductor. So therefore, the rule that we should, the law that we should apply to the circuit should be KVL. Yes. That's what I suggest you do. Let's do the first one. So that's why I explained right here. So let's do KCL, right? So KCL on this node right there. That's U of t is equal to IC plus IL, right? So from KCL on that node gives you U of t equals to IC plus IL. That's what I should have. This is low. I'm not sure what's going on here. Hang on a second. There you go. All right. So by KCL, U of t is equal to IC plus IL, right? And right away from here, I know, excuse me, I know that IC is equal to C dVC dt, right? And so I'm going to isolate that dVC dt to the left-hand side. Why? Because again, the equation is x dot equals to AX plus BU. So I want the x dot to be on the left-hand side of the equation. I get the x dot from here. That's why I move IC to the left-hand side of the equation. See that? That's equal to minus IL plus U of t. Okay. And from there, I know that IL is C dVC dt is equal to minus IL plus U of t. And I know that this dVc dt is none other than x1 dot, right? So now I have C x1 dot equals minus IL plus U of t, right? And from there, I can solve for x1 dot, right? Which is right here. Now, once you get this equation, once you obtain x1 dot or any x dot on the left-hand side of the equation, then check, number one of the steps is to check on the right-hand side, right? Check to see if on the right-hand side, you have only state variables and input, or either one. It doesn't have to be both, but either X or U or both, right? Is that what we have here? The answer is yes, right? If you look at the right-hand side of the equation, I have x2, I have U of t, right? So x2 is our state variable, and U of t is our input, right? So that means it satisfies that requirement right there, right? Okay, so this is good. That means you're done for x1 dot, done. Okay. Any questions so far? If not, let's do the second x dot equation. Remember, we have two state variables, right? So you need x1 dot, x2 dot. x1 dot is done. Let's do x2 dot. Remember, x2 dot, we get it from KVL. So let's see which KVL should be applied here, right? So I would say apply KVL around the right-hand loop, because I don't know what the voltage is across that current source, right? So I'm just going to do it around the right-hand loop right there, right? So if you trace the polarity there, you get VC is a rise, voltage rise, and then VL is a drop, and then voltage across resistor, right? That's another drop, right? So when you write the equation, you should get right here. VC is equal to VL plus V out. And V out is equal to R times IL, right? And I know that VC, right, that's our state variable x1, isn't it? VL is the one that we get the IL dt, right? That's what we're looking for, right? We're looking for the first derivative, right? And then move it to the left. That's what I did. I moved VL to the left, right there. L d IL dt. Now I bring VC to the right, and I get VL equal to VC minus V out, right? And then VC by itself is already x2, or sorry, x1, and then V out by itself is R times IL, right? So then now I can rewrite the equation such as this right here. Divide both sides by L, and you get x2 dot, right? Because that's DIL dt, that's our x2 dot, equals BC, which is our x1, and R, which is just a constant, and IL, which is our x2, right? And then you have to divide both sides by L to get rid of this L from the left-hand side. And you get 1 over L times x1 minus R over L times x2 for x2 dot equation. Okay. Now, now that we have the equation where on the left-hand side we have x2 dot, and now you need to check to make sure that on the right-hand side you have only state variable or input or both, right? Is that what we have now? The answer is yes. You can see on the right-hand side I have x1 and x2 only, nothing else. That means we are done for x2 dot equation. All right. So for this example, it's not bad, right? By just one step for KCL, one step for KVL, and you get the two equations for x1 dot and x2 dot, right? What about the output equation? Well, output is defined to be voltage across the resistor, right? Right here. That's our output is equal to IL times R, right? So y is equal to IL is our x2, so that's r times x2, right? Y is already on the left-hand side, and then r is a constant, as I said, and then x2 is already on the right-hand side of the equation, right? So check to see whether or not on the right-hand side of the equation you have only state variable or input or both. In this case, you only have one state variable, which is good. So you're done with the output equation. So to summarize, you have three equations. Now you can put them into a matrix equation, right? I've already transformed those into matrix equation, but if let's say I write the equations first, it should be x1 dot equal, what was it? I forgot. Oh, I have it right there. Is equal to minus 1 over c x2 plus 1 over c u of t, right? And then x2 dot is equal to 1 over L x1 minus r over L x2, right? And then y is equal to r x2. These are the three equations, right? Then you can transform those into matrix equation, right? Any questions? Then once you form the state space equations, you can check, right, the size of the matrices, right? Matrix A was supposed to be 2 by 2, and that's what I have, 2 by 2, right? And then matrix B, what was matrix B? N by I, right? N by I. So 2 by 1. That's what I have, right? 2 by 1. 2 by 2, good. 2 by 1, good. All right, matrix C. Matrix C is, matrix C is, what is it? O by N. O by N is 1 by 2. Is that 1 by 2? It is, right? So let's check, right? How about matrix D? Matrix D is O by I, right? O by I. O is output, only 1. I is input, only 1. So that's 1 by 1. Well, you don't see it here, right? But there is actually a D matrix, right? Which is a 0 matrix times the input. So you can see the 0 matrix is 1 by 1. And because this is the 0, we don't really need to write that. Any questions? All right. Let's look at the second example right here. Now let's do this faster, right? Okay. Let's answer this question first. How many inputs do we have? Anybody quickly? How many inputs? 2. Very good. How many state variables?
2.
2. Very good. So, and then output is defined to be voltage across the resistor right there, right? So now by knowing that we have 2 state variables, that means A should be 2 by 2, B should be N by I, 2 by 2, right? And then C should be O by N, so that's 1 by 2, and then D would be O by I, 1 by 2, right? Okay. O by N, let me double check. O by N is 1 by 2. O by I is 1 by 2. Yes. Okay. All right. Let's choose our x1 to be IL, our x2 to be VC. Right? You don't have to choose this way, but for my answer, I choose x1 to be IL, x2 to be VC. Therefore, x1 dot would be dIL dt, right? And x2 dot would be dVC dt, right? And then for dIL dt, as we already learned earlier, let's do KVL. Let's do KVL around the left loop, right? Because that's where you have the L right there, right? Left loop. So from there, I get this equation right here. V1 minus L dIL dt minus VR equals to 0. And I move the dIL dt to the left side of the equation. And I have the first equation for x1 dot. As you can see, this is x1 dot equals the right-hand side of the equation, right? Now tell me, are we done with x1 dot? Yes or no? Is this a valid state space equation? Is it valid? The answer is, anybody? Nobody wants to answer? 513 people. X dot is equal to AX plus BU. Does that satisfy the requirement?
Yes.
Yes. You sure? The answer is no, right? Because look at what we need. We need AX plus BU. Is that what we have here? On the right-hand side?
No.
No, right? Why? Why not? Which one is a problem?
VR.
VR, yes. So VR, that's a no-no, right? We cannot have VR. Why? Because VR is neither X nor U, right? That VR is not state variable, and VR is not input either, right? So therefore, we need to do some more work on VR, right? So let's leave it here for now.
Hey,
We'll
Professor, I have a quick question.
Yeah, go ahead.
What's the output for this equation? Isn't VR the output?
Yeah, but look, on the right-hand side of the equation, do you have output?
Oh, sorry. Yeah, you're right. My bad.
Right.
Yeah.
So there's no y on the right-hand side of the equation. That's why it is still invalid. Right?
Sorry, I haven't had my lunch yet.
Oh, it's okay. I haven't had my lunch either. I'm fasting, remember? Okay. Let's see. How about so yeah, like I said, this is not done yet, right? So let's leave it there for now, and let's look at the equation for VC. Right. So VC, as you know already, we need to apply KCL, current. Right. So I can do KCL at that node, right? So let's see. That would be, what is that? IL plus IC is equal to IR, right here. Oh, sorry. Let me scroll down a little bit. Yeah. So you can see IL plus IC. This is our IC minus IR is equal to 0, right? And then you want to put the first derivative to the left-hand side, right? Just like that. And the remaining terms should be on the right-hand side, and then get rid of the C, right? So you divide by C, and you get the equation number 2, right? Now let me ask you this again. Is this a valid state space? The answer is
No.
No. Very good. Why not? Which one causes the problem here?
IR.
IR. Very good. IL is fine, right? IL is our X2, X1. See that? So IL is fine. And we want X and U on the right-hand side, right? X is right there, so that's good. But IR is neither X nor U. So therefore, this is not good, right? So we need to work more on these two equations. Okay. So what can we do? Well, we used KVL around left-hand loop. We did this loop. We did KCL. So maybe if I apply KVL around the other loop, maybe that would solve the problem, right? So let's see. On the right-hand loop, you have KVL equals VR. Let's see if that's true. There's a voltage rise, voltage drop, right? So VR plus VC equals to V2, right? Right there. Where is it? My cursor? All right there. Ah, there. So VR plus VC is equal to V2. So therefore, VR is equal to V2 minus VC, right? So I want to get rid of VR, basically, right here, because we know that that causes the problem, right, for the first equation. So let's see if I do KVL around the other loop, right? Let's see if I can substitute that VR so that on the right-hand side of the first equation, I only get X and U. Well, let's see. VR from the KVL around the right-hand loop gives us V2 minus VC. Think of it, right? If I substitute VR with this equation, would that be good for our state space or no? Yes or no? The answer is yes. Why yes? Well, because look, V2 is our input. That's U, isn't it? So that's good because U is what we want on the right-hand side, right? How about VC? Is that good to have on the right-hand side? Yes, because VC is our X, right? X2, right? And that's what we want on the right-hand side, X, right? So now that's what I'm going to do. Because I know by using the right-hand loop KVL, actually I get a good equation for VR. And that's what I did right here. You see that? I replace VR with V2 minus VC. Right? This used to be VR. Right? Once I substituted that, then I have a new equation for x1 dot, which is equation number 4. And go ahead and check. On the left-hand side is x1 dot. That's awesome, right? On the right-hand side, I get x, which is good. And I have v1, which is good because that's u. And another input, which is v2, right? So that's good. This is valid, right? So that's good. We are done with x1 dot. Any questions? We still have problem with the second equation, right? x2 dot. On x2 dot, I have IR. That's the one that's causing the problem, right? I have IL, which is good, but IR, which is an issue, right? So let's see, how can we get rid of IR? Well, I know that IR, by Ohm's law, IR is equal to VR over R, right? Have you seen the equation for VR before? The answer is yes. We just derive it right here. So if I replace VR with V2 minus VC, then we should be okay, right? So that's what I'm going to do. Right? I'm going to replace IR with V2 minus VC over R, right? With this equation. Make sense? So that's what I'm going to do. And right here, right, this used to be IR. I replace it with V2 minus VC over R, right? And then look at the algebra, right? Hopefully that's correct. Is it? Minus, yes, it is correct. So then now I can rearrange the equation such that on the left-hand side, I get x2 dot. On the right-hand side, I get x1, x2, and v, right? U right here, and x right there. So now this is valid, right? I am done with x2 dot. Any question on this? Yeah. Output. So output is y, right? Y is equal to VR, right? So we already have the equation for VR, right? That's V2 minus VC. So here's our output equation. So ask yourself a question. Is this a valid state space equation? On the left-hand side, I have y. It has to follow y is equal to cx plus du, right? On the left-hand side, I have y, so that's good. On the right-hand side, I need x or u or both, right? What do we have here? On the right-hand side, I have v2, that's our x, right? Oh, sorry, our input, sorry, that's our input. And then I have vc, which is our x, right? I forgot which x is that. that would be x2, right? So that's good, right? Because on the right-hand side, I have x and u. Therefore, you don't have to do anything else for the output equation. We already got the equation from before, and that's going to be minus x2 plus b2. All right. From here, you have the three equations that you need, and you just transform those into matrix equation right there, right? What did I say about the size of the matrices? I forgot now. A, because it's two state variables, it should be 2 by 2. That's what I have, 2 by 2. B should be O by N, 2 by N, sorry, N by I, 2 by 2. Input is 2, yes, 2 by 2. Is that what I have? Yes, 2 by 2, right? And then C should be O by N. There's only one output, two state variable, 1 by 2. It is 1 by 2, right? Right there, check. And lastly, D. D should be, what was it again? O by I believe, right? O is only 1, I there's 2. So it should be 1 by 2. Is that what I have? Yes. Check. All right. Hopefully that's clear. Any question on this? What if in the previous example, we add another output defined to be the current through the capacitor IC? Will this change the X dot equations, i.e. the A and B matrices? The answer is no, since matrices A and B are independent of the outputs, right? Remember A, see that A is N by N. There's no O there. So if you add another output, it's not going to affect A, right? If you look at B, there is no O there. So therefore, adding an output will not affect the matrix B. But however, it would affect matrices C and D, because as you can see, matrices C and D, they are depending on output right there, right? So that's what I said right here. Will this change the output equation? And the answer is yes, since matrices C and D are governed by the outputs. So all you need to do, you don't need to rederive A and B. You don't need to rederive x1 dot, x2 dot if you have homework such as this, right? All you need to do now is just to add the output, rederive the output equation, right? So you just here, the two outputs are y1 is equal to VR as before, and now I add another one, y2 is equal to IC. Let's just say, right? So y1, we're already done with it. I won't have to go through the derivation. Y2 is the one that we just added, right? So y2 is equal to IC, and we know that IC is equal to C dV C dt, right? And C dV C dt is Cx2 dot, isn't it? So do we have the equation for x2 dot? Yes, we do, right? That would be this one right here, x2 dot. You have x2 dot equation. So now you just need to plug in the equation into y2 into x2 dot. Right? It's going to be a long equation right there. Right. It's so slow here. Hang on. Okay. So that's what I have right there. X2 dot is already obtained from the previous derivation. All you need to do now is just to plug in all of these into Cx1, x2 dot, right? Just substitute all of these into here, right? That's what I have right there. And at the end, I have one more equation for the output. See that? Okay. So check the size again. I don't need to check A and B. This is already done. They're not affected by the output. But C and D, they do, right? They are affected by the output. So you do need to check the size of matrix C and D. C is, I keep forgetting, O by N, I believe, right? So that's 2 by 2. 2 output, N is 2 state variables. D is O by I, 2 by 2. Is that what I have? Yes, 2 by 2, 2 by 2. Awesome, awesome. Right. Any questions?
Why is it in the before you add the second output for the A and B matrix, it's x dot 1, x dot 2 equals instead of y1 and y2? Oh wait, never mind. I read that wrong. Never mind.
Okay. Hang on. This is did I type it wrong here? Actually, I checked the wrong ones, right? Sorry. This is A. This is matrix A. This is matrix B, right? What I need to check is these two matrices, right? So matrix C is 2 by 2. Is that correct? 2 by 2? It is correct. And then matrix D is also 2 by 2. That's correct, right? Yeah, sorry. Yeah, this is the same x dot equation that I had earlier, right? Earlier, I was trying to check C and D, but I checked the wrong matrices, but it happens to be 2 by 2 for both. Okay. So I should check this equation against these sizes. Okay. Any questions? Any other questions? No? All right. Now, when I teach 302, I always emphasize the last check right here, because notice that for matrix D, look at the first column is 0 and 0, right? Many students, not a few, but many, it's not a few, but quite many students, they end up with just writing this way for the D matrix, which is wrong, right? So even though there's zeros, you still have to include those, right? And you can clearly see once you check, right, that D matrix D should be 2 by 2, and you see, oh, that's 2 by 1. That's not right, right? So what am I missing? So most likely the zeros. Okay. Any questions? All right. Okay. I am done with reviewing state space equations. Hopefully that's a good refresher for all of you. Any questions? If not, let's look at state space averaging method of our DC to DC converter, right? As we know, for DC to DC converter, let's just look at the basic ones, right? Buck boost and buck boost. For those circuits, there are only two states, right? State where the switch is on and the state where the switch is off. So therefore, if the circuit changes its state, how do you derive the state space equations, right? Because the examples that we have earlier, there were no states, right, of the circuits. It's only one state of the circuit, right? There's no switch. Now circuit is just going to be like this in steady state or in transient, right? It's just going to be like this, right? There's no change in the state of the circuit. But in DC to DC converters, right, it's different, because now we have a circuit that looks different when the switch is on from when the switch is off. Right. So how do we deal with the steady state, not steady state, how do we deal with the state space equation for a circuit that changes states? Right. So let's take a look. So for DC to DC converters, for circuit that have different states depending on the state of the switch, then we can do a method called average model of the state space equation, right? The average model. I know some of you who took 513 already learned this. So for some of you, this would be another review, but for the rest of you, this is probably something new, right? Okay, let's use a buck converter right there, right? A buck converter, the switch could be modeled this way, right? Either the switch is on A or the switch is on B, right? If it's on A, that's when the main switch is on, the diode is off, right? When the switch is on B, that's when the diode is on, the switch is off, right? So let's derive the state space equation for both states, right? Let's start with when the switch is on. When the switch is on, meaning the switch is on A, we have this circuit, right? That's when the switch is on. Oh, I have it right here. When the switch is on, right? That's the circuit. That's how the circuit looks. And again, our objective here is to get x dot is equal to ax plus bu. And here, since this is one of the two states, I'm going to call A1 and B B1, right? To indicate that this is from the first state of the two states, right? Okay. Our input, there's only one input, right? And there are two state variables, IL and VC, right? So let's write the equations right there by KVL and KCL. Oh, and I have to show this circuit. Let's see if I can fit the two. Yeah, right there. Hopefully you can still see. If you apply KVL around this loop right there, right, you get, what is it? V of G, that's the input, equals the drops VL and the drops VC, right? So therefore, well, from here, I know I get LDIL dt from here. So I'm going to move VL to the left-hand side. That's what I did. See that? And VC, see that VC right here? I call this node voltage V. So that's why I simplify the name to V. So instead of VC, it's actually V. Right. Notice that V is also the same as the output voltage, right? Because they're in parallel, right? VC is equal to V out. Right? Okay. And then by KCL, to get dVc dt, I put KCL on that node right there, right? So clearly from there, I get IC is equal to I minus VR, right? So let's erase this. There, right? So by KCL, I know that I is equal to IC plus IR. Yes. And where do I get the X dot? From IC, right? From here, I get dVc dt. Right, that's actually C dVc dt, right? So that's why I place IC to the left-hand side of the equation right there. Right. And IR, right, we know is equal to VC over R. That's great, right? Because VC is our state variable. So that's good. But VC is equal to V, right? That's what I put right here, right? That based on the KCL, I get C dVc dt equals to I minus V divided by R, right? Now, are these good? Are these valid state space equation? Let's check, right? Other than we have to divide both sides by L and by C, let's just check the right-hand side. That's our input, so that's good. That's our state variable, that's good, right? So this is valid state space equation, okay? The second equation, I is our X, right? That's IL, and then V is our state as well. So that's good also. Okay. Is that clear to everybody? So these two are valid. So I'm done. Basically, I'm done writing x1 dot and x2 dot. So I transform this into matrix equation right there. I'm still leaving the L and C on the left. It doesn't matter. You can, at the end, you have to divide both sides by L and C anyways, right? So then you have this equation, right? So either way, right, either this way or that way. So you can see I have now the state space equation, just the x dot, right? Just the x dot on the first state of the circuit when the switch is on. Any questions so far? Let's do the second one. When the switch is off, what we do here is we are disconnecting the input. So you can see the input is disconnected from the circuit. So the circuit now changes to a new circuit, right? No forcing function, right? There's no independent source right there. And you can see we still have two state variables, right? No input, and there is still output over here, right? Okay. So what kind of a state space equation can we get from the second state when the switch is off? Well, we can do the same thing, KVL and KCL, right? KVL states that VL is equal to minus V, because that's plus minus, right? That's plus minus. You can see that VL is equal to minus VC, right? Which is equal to minus V, right? So that's what I have right here. Easy, right? And then KCL, same as before, it doesn't change, as you can see, right? By KCL, just like before, IL, which is what I call I, is equal to IC plus IR, right? So, and we know IC is equal to C dV/C dt, and IR is equal to V over R, right? So just substitute that into here, and you get, just substitute that, not substitute, sorry, rearrange the equation such that the dV/C dt is on the left, right? The remaining on the right, and you get this equation right there, right? As we already know, this is the same as before, right? No difference than before. So we know this is already valid, right? How about the first one? It's minus V, that's also valid, right? But that's our X that's one of the state variables. So valid. So now we can write those two equations, right? These two equations into matrix equations. And that's what I have right here, right? With L and C on the left still, or you can just divide both by L and C, and you get another state space equation. Similar, I mean the same. Those two are the same, right? And this second one, I call it A2 and B2, right? X dot is equal to A2X plus B2 times BG, right? So now I have two state space equations that describe our buck converter, right? So our buck converter has two different state space equations, right? One that is derived when the inductor is charging, right? The inductor is still charging. That's during on time of the switch, T on. And you can see that the other state space equation happens when the inductor is discharging. That happens during T off, right? The off time of the switch. And as we learned from EE410, right, duty cycle is equal to T on over T. So therefore, T on is equal to dt, right? And then T off must be 1 minus D. Oops, sorry. T off must be T minus T on. So T minus T on, well, T on is dt. So therefore, 1 minus D times T for T off, right? Because since we're averaging, so we have to average it by the entire period, right? So therefore, the T should disappear, right? Because you divide by T, right? Okay. So then what we're going to do is that since we have two different states, right? How can we get the overall state of the of the buck converter. So this is what's called average state space model, right? So you basically averaging the two, right? Averaging the two state space equation that we derive. You add the two, and then you divide by the period, right? That's how you average, right? You average by summing the two and then divide it by the period. So that's what I did right here, right? So because we divide by t, as I said earlier, therefore t on is going to be just d, and t off is going to be just 1 minus d without the t, because we divide it by the entire period. Make sense? So for the first state space, right, we'll multiply it by the duty cycle, right? For the second state space, we multiply it by the 1 minus d, right? And that's how long it takes, right? That's how long it takes for each state. So that's what I did right here. The first state space equation, I'll multiply both sides by d, right? And you add with the second state space, and you multiply it by 1 minus d. You see that? And then you add them up. You just add them up. When you add them, you get this equation right here, a matrix equation. And you can see on this one, you can see the d cancels, right? The d cancels, and this one does not, right? The equation is still there, but on the left hand side, you get 1 times the whole thing, so that's going to be the same, right? And over here, you also have 1 times this whole thing. That's why you have the same matrix equation, right? And on the last one, if you multiply out, you get, what is it? You got to multiply d times 1, that's d, plus 1 minus d times 0, that's 0, isn't it? And then for the second one, d times 0 is 0, plus 1 minus d times 0, that's 0, right? So that's equal to d and 0. That's what I have right there. Right. Any questions? So after I add and then average, right, I get our state space averaging, the other way around. I have the average state space equation right there of the two states. Right. So these state space equations, again, is an average state space equation. This would represent our buck converter with the two states, right? So that in steady state, to prove that this equation is correct, right? In steady state, di over dt would be constant. Oh, not constant, sorry. I would be basically no more changes, right? So therefore, di dt would be 0, right? State space in steady state. And then dv dt, no more changes. So therefore, dv dt is going to be equal to 0, right? If that is the case, then go ahead and plug in 0 to di dt and plug in 0 to dv dt. Go ahead and do that. And then you can call I to be just capital I for steady state, DC basically, right? That's the DC component. And then V will be just capital letter V, right? So that's what I did right here. And the same thing as, duty cycle is already steady state. And again, plug in zeros to both the IDT and the dVdt. And you get on the left-hand side of the equation, right? What do you get? You get L times 0 plus 0 times 0, that's 0, right? 0 times 0 plus C times 0, that's also 0. And on the right-hand side, you get the same thing, but go ahead and carry out the equations. For the first row, 0 is equal to 0 times I, that's going to be 0, plus minus 1 times V, so that's minus P, plus dVg, right? That's from the first equation. So that's 0 equals to minus V plus dVg, right? So from here I get V, which is our output, by the way, right? Remember V is our VC, and VC is the same as output, is equal to D times Vg, steady state, right? Is that what we expected from a buck converter? Steady state, yes or no? For a buck converter, what is the transfer function V out over V in equal to? Anybody?
Wouldn't it be duty cycle?
Yes, duty cycle. Isn't that what we have here? Right? So V out, remember V is equal to V out, right? It's actually equal to V out. It's actually equal to VC. V is equal to VC, but VC is the same as V out, right? So that equation right here is actually V out equals to D. And what is our VG? VG is our input, isn't it? So therefore, you can see that V out over V in is equal to D, as expected for steady state, all right? Okay, now for the second equation right here, right? Let's multiply out these numbers. So 0 is equal to 1 times I, that's equal to I, minus V over R plus 0 times VG by 0. See that? So now I have I equals to V over R. Ohm's law, yes, but is this what we're expecting from a buck converter? Keep in mind that I is from the small case I. What was the small case I again? In the initial circuit, isn't that IL, right? So I is equal to I, right? And in steady state, you can see that I, or IL average, this is actually the DC component, right? IL average is equal to V over R. What is V again? V is our output, isn't it? Divided by R. Is that what we're expecting from a buck converter?
Yeah.
Yes, right. Remember, especially if you've taken 410, you should know this, right? A buck converter has, on the output side, has this, right? That's our output voltage. That's our R. That's our C. That's our L. This is our current IL, right? The average value of IL in steady state is equal to V out over R, isn't it? As you learned from E410. What happens with IC? Am I ignoring IC? See, from KCL, yeah, from KCL, I know that IL is equal to IC plus IR, right? But in steady state, average value, IL is equal to average value of IC plus average value of IR, right? Am I ignoring IC? I know that IR is equal to V out over R, right? But what about IC average?
ASB.
ASB, yeah, very good. Amp second balance states that the average current through the capacitor in steady state should be 0, right? So I'm not ignoring it. It's just the fact that IC is equal to 0. That's why this right here validates, right, that this equation is correct from a buck converter. Because again, for a buck converter in steady state, the average current through the inductor must equal to I out average, which is V out over R. So that's good. All right, so let's stop the video first. There you go. Okay, as you already know, another way of modeling our circuits or system in general would be to use transfer function. Okay. Let's see. So transfer function for DC to DC converters, specifically for DC to DC converters. So in DC to DC converters, ideally the output voltage is a function of the input voltage and the duty ratio. And practically speaking, the output voltage is also a function of the load current, right? Yeah, the load current right here that should also affect the duty cycle based on Ohm's law, right? The more current you draw through the load, the more drops you see across, the more drops you'll get across each component, right? So therefore, as you learned from last week, right? As we are stepping up the load current, voltage drops, right? By Ohm's law, okay? The output voltage is regulated by sensing the output voltage. The measured output voltage then compared to a reference switch yield an error signal. And the error signal itself then is being used to adjust the duty cycle, duty ratio to compensate for variations in input or the load, right? So block diagram wise, here is showing a voltage mode control. It's not current mode control, right? It's only voltage mode control. How do I know that? There's only one loop, right? So that's the simplest type of controller. You only have one loop. And you can see that we have the sensor sensing the output voltage, which is then compared with a reference voltage, right? And the output of which gives us error signal, which is then processed through PWM controller or PWM circuit that would provide us with the duty cycle. That duty cycle then feeds into the driver circuit, which is basically the muscles, right? That would provide the action of the switch to turn on or turn off. All right. In its basic form, the power supply. Oh, hang on a second. I forgot something. Can you hear me?
Yep.
Yes.
Yeah, I forgot to put on my headphones. Well, you can still hear me though, right? Earlier?
Yes.
Okay, good. Oh man, I forgot. All right, sorry about that. Where was I? In its basic form, the power supply control consists of output voltage sensing device, a compensated error amplifier, and a pulse width modulating switch. So in its basic form, a voltage mode in this case, it would our block diagram, transfer function block diagram, should have the switch, including the diode. It should have a block that would represent the output filter, compensated error amplifier, as well as the PWM circuit. So if I were to transform this from circuit type of diagram to control block diagram, then I would get something like this right there. Okay. So this is something that you've seen right before. You took 302 and you learn about feedback, system and the block diagram that goes with the control systems, right? So you have the input, which is our reference, right? And also the actual input voltage. So there are two inputs, the actual input voltage and the reference voltage, right? And then let's say we start from the input voltage, right? It is now applied to our switch, and the switch turns on and off. And along with the duty cycle, we get our portion of the input voltage, PS times D, and then we send that signal into filter and load to give us the output voltage, right? Which is then monitored, right? Sensed through this feedback system. There could be a gain here, of course, but I'm ignoring that gain. That gain is going to be a constant gain. It goes back to the summing junction, right? Where I compare that with VREF, right? Of course, if you have the gain on the back here, on the feedback, that gain would be a fraction, right? A fraction of the output voltage. So therefore, the VREF would also be size based on the fraction of the voltage we want to compare with, right? So if let's say that fraction gives us 1 volt, then the VREF would also be 1 volt, and so on and so forth, right? And again, as you saw last week, or actually on Monday, this VREF is internal to the controller, right? And the difference between the two signals, the actual output voltage and the reference voltage, that gives us the error signal, right? From error signal, it fits into compensated error amplifier, and it gives us the output from the error amplifier that gives us, actually this is another error signal from the error amplifier, which is then feed into our PWM circuit, which is then produces duty cycle, right? And you can see now we're back to the starting point, right? Okay. All right, so that's the block diagram. Any question on the block diagram first? Control loop stability. So for control loop stability, we can actually open the loop, right? We can open the loop, basically break the loop right here, and we can take a look take a look at the stability of the control loop by open loop characteristics, right? So open loop characteristic requirements for performance and stability of the control loop in power supply should be that at low frequency, the gain should be large. So low frequency, the gain should be large. And this makes sense, right? Because we have DC to DC. Low frequency means DC, right? Basically, right? So the DC gain should be large such that the steady state error is small, right? And then the gain at higher frequencies, right? So if you take the body plots of the open loop system, right? You break that feedback. The gain at higher frequencies should be small, right? Which again makes sense, right? Because again, we want DC to DC converter. We don't want the high frequency to be present at the output, right? In order to do that, we need to have a very small, gain, minus dB gain for the high frequency components. So to me, this makes sense. Any question on these two first? So again, low frequency, high gain, high frequency, low gain, right? Always the opposite, right? That's the way I memorize this. Low frequency, high gain, high frequency, low gain, right? And then those are in terms of the gain. In terms of the phase angle, right? As you already know from 302, that the angle should be less than 180 degrees when you break the loop, right? When you break this, what is my, all right. When you break this loop right there, open basically, right? The angle at the output should be less than 180 degrees. If it's equal to 180 degrees, that's not good, right? Why not? If let's say that at this point, the angle is 180 degrees. Why is that bad? Either 180 degrees or minus 180 degrees. Why is that bad?
Would that be negative voltage?
Nope. Almost. Remember, we're breaking this loop, right? So if you have 180 degrees already on the output, that's going to be bad it's not going to be stable. It's going to be unstable. Nobody remembers from control system class? No? All right. So, all right. Let's review this quickly. There you go. Let's just simplify our block diagram, right? Like this. Let's just use unity feedback for now, just to keep it simple. Right there. So my question is, why is it that when the output has 180 degrees angle or minus 180, typically minus, right? Because it's lagging system typically. This is bad. When I break the loop there. So I break the loop. Why is it bad? The reason being, if you already have 180 degrees, or let's just do minus 180 degrees, right? If let's say at this point, I already have minus 180 degrees when the loop is broken like this, then what happens after I connect the loop back? What do you think? That's my hint right there.
It's going to act like positive feedback.
That's correct. right? So keep in mind that typically, or most of the systems, right, are usually utilizing negative feedback, right? Negative means on the feedback path, there's a negative sign right there, right? Negative means what? Adding another 180 degrees or adding another minus 180 degrees, right? So this by itself, let me erase this, right? That negative sign by itself is already minus 180 degrees, right? When a signal comes, let's say I put a signal X, right? And that signal X now sees that minus sign. That means we have minus X, right? Or in other words, minus X is equal to X at 180 degrees, right? Or X at minus 180 degrees, right? Again, I'm just going to use minus because, typically we have lagging systems. Agree? So that negative sign is already saying I'm going to add minus 180 degrees phase angle to whatever comes into the summing junction, right? So imagine if the signal we have from the output already has minus 180 degrees, then we close the loop, right? Then what happens then? You have a signal, let's call this X now, a signal that has already 180 degrees phase angle. Now it gets into this feedback and it sees the negative sign. That means you add another 180 degrees, right? Now you have X at 360 degrees, right? Is that good or bad? Of course, that's bad, right? Because now instead of V, see this signal right here, call it Y. Instead of having Y equals to V ref minus X, now you actually add instead of minus. Now it's actually adding. Now this is no longer the case. It's going to be V ref plus X, right? Because that negative sign is being canceled by this 180 degrees, right? That negative sign now becomes positive, becomes adding, right? Because now you have 360 degrees. Make sense? You remember this from 302? In fact, do you remember the equation for phase margin and gain margin? Gain margin is defined to be in body plots, right? 0 dB minus, what is it? Minus the phase angle at crossover frequency, right? At crossover frequency. Okay. And what is special about crossover frequency? Crossover frequency is the frequency at which the gain is equal to, anybody?
0 dB.
0 dB, or in linear gain is equal to 1, right? That's important to know, right? And then phase margin is equal to phase angle at, this is not phase angle. I know there's something wrong there. Gain. Sorry, wrong way. Gain margin is 0 dB minus the gain at which the phase angle is minus 180 degrees. There you go. Sorry about that. And then phase margin is phase angle at the crossover frequency. There you go. Minus 180 degrees, which is basically phase angle at crossover frequency plus 180 degrees, right? And as you know, crossover frequency is special because the gain at crossover frequency is 1 or 0 dB. Right. Now, in EE302, I explained why it is 100. Why is it that stability points are defined to be 180 degrees and 1? You notice that? Why is it that see that 180 degrees and 1? Why is it that stability in frequency domain are being represented, or not being represented, are being determined by those two values, by angle equals to 180 degrees or minus 180 degrees and gain equal to 1. Why? Why not 45 degrees and 2? Or any other angles and other gain? Why? Well, there must be reasons for that, right? And reason I already actually explained one of them, right? If let's say you have, again, this is just a review from 302, right? If you have a transfer function like this, right? Vref plus minus, right? Like this, right? Now, if you have a gain of 180 degrees, now, okay, sorry, phase angle of 180 minus 180 degrees, we already know it's bad, right? And it will be even worse if the gain is equal to 1, right there. If the gain is equal to less than 1, let's say a gain of 0.01, then there might be, then we still have a chance of having a convergence instead of divergence, right? Because anytime you add, remember 180 degrees when you close the feedback loop becomes addition, right? But even if you add the two signals, if the gain is very tiny, right, then it is possible you still have convergence on the output instead of divergence, right? Now it is a problem when the gain is 1 or larger, right? So let's just put 0.01 first, right? So your x is right here, right? So let's say this is your y, right? So your y is equal to vref minus x, but because it's 180 degrees, you actually have a plus now, right? But then that y goes through another transfer function and you multiply it by 0.01. So now it becomes very tiny, right? Signal, because you multiply it by a small fraction. So every time it goes back to the loop, you multiply by even a small, this signal becomes even smaller and smaller and smaller, right? Because you keep multiplying it by 0.01, even though you add the two signals instead of subtract, right? Make sense? Now this becomes a problem if this gain is 1 or larger, right? Because then the signal right here, right, the output basically, V out, here V out is equal to 0.01 times y, right? So anytime it goes back, you always multiply by 0.01, so it becomes smaller and smaller and smaller, right? What do you call it? The error signal becomes smaller and smaller and smaller. So that's okay. But if you always multiply by 1, right, then every time it goes back, right, it will add more. It will add more, right? It becomes bigger and bigger because you always multiply by this by 1, and then when you go back to the loop, you always add to the same number, right? Doubling it. Basically, you're doubling it every time, right? So now you have a divergence problem there. Make sense? Oh no, hopefully it does. If it, of course, it makes even worse if the gain is larger than 1. I mean, try 100. So every time it goes back, right, the error signal is already bad because you add, and then you multiply that bad signal by 100. That's even worse, right? And it goes back, right? You add, it's already bad, and then you multiply by 100 again. That's even worse, right? So that's the way I explained it in 302, is that this condition right there, right, defines the limit for the gain, which is 1, right? So that's the borderline is 1, right? So the borderline is 1, right? Or the threshold is 1 for the gain. That's why, right, we know from these explanations that our control system will be bad if the gain of this process transfer function is larger than 1, or limit is 1. Basically, 1 is the limit, while the angle is minus 180 degrees. That's why these two numbers are important when calculating phase margin and gain margin, right? In case you're wondering why in those equations we use 180 degrees and 1, now you know the answer. Okay. Any questions on that? All right, so going back to here, right, the open loop phase shift at the over frequency phase margin must lag by less than 180 degrees. Now you know why it says less than 180 degrees, right? A typical phase margin of at least 45 degrees is usually adopted. So at least 45 degrees. If the lag is 180 degrees, negative feedback provides another 180 degrees, resulting in a total of 360 degrees or 0 degrees. You already know because I've already explained this, right? This is not desirable since a gain of 1 and a phase angle of 0 make the loop unstable, as I already explained earlier. Right? Any questions on this? So here is how you calculate gain margin and phase margin from body plots, right? If you want to calculate gain margin, you always go to the phase plot first, always the opposite. Gain margin, start from phase plot. What do you look for from phase plot? Look for the intersection of the phase plot with 180 degrees. Remember, that's the border line, right? For the phase angle, right? 180 degrees. So once it intersects, the intersection right there, right? So again, for gain margin, right away you look at the opposite phase plot, which is phase plot. Look for the intersection of the phase plot with minus 180 degrees. And that intersection, if you draw a straight line up, right there, you can see the gain margin right there, right? The difference between, right, phase angle, right? That's not phase angle. The difference between gain, I keep changing this, gain at which the angle is 180 degrees, right? The difference between 0 dB and the gain at which the angle is minus 180 degrees. That gives you gain margin, right? Basically, this from here to here, right? Phase margin, the other one, if you're looking for phase margin, always look for the opposite plot at first. Phase margin, that means you look at the gain plot first. What are you looking for in the gain plot? Look for the other borderline, right? What is the other borderline? Gain equal to 1, right? In dB, that's 0 dB. That's the limit, right? That's another borderline. So find the intersection of 0 dB with gain plot. That's what we call crossover frequency, right? Once you get the crossover frequency, find the phase angle at that frequency, which is right here, right? So the difference between minus 180 degrees and the phase angle at crossover frequency defines phase margin, right? So phase margin is equal to phase angle at crossover frequency plus 180 degrees, right? This plus actually comes from minus and then minus, right? Let me just do it correctly. Minus 180 degrees. There you go. Okay. Any questions? All right. So transfer function for a buck converter would have these blocks: switch transfer function, filter plus load transfer function, PWM transfer function, and error amplifier transfer function, right? So basically I have this block diagram, and I want to be able to derive the transfer function for each of these blocks. Right? As you can see, I have four of them, right? Switch, filter and load, PWM, and compensated error amplifier. Okay. So let's look at the switch transfer function first. Right? In the buck converter, the switch block consists of the switch itself and the diode, just like this, right? That's the input stage of a buck converter. Right? Buck converter looks like this. Oops. This is how buck converter looks. There, assuming that the input voltage is constant, right there, Vs, then you can see that Vx right here, right, is equal to duty cycle times Vs, right? So voltage at this node must equal to, average value wise, is equal to Vs times duty cycle. right? Let's keep in mind that this switch turns on and turn on and off, on and off. So therefore, if the input is a flat input, Vs, then Vx would be like this, depending on the duty cycle. So the average of this, Vx is equal to duty cycle times Vs, right? So right here. So therefore, Vx over Vs is equal to D. So I'm done. I'm done with the transfer function for the switch block. Remember, I have a switch block, right? So inside the switch block, the transfer function is D. All right. And we know that D, value of D is between 0 and 1. Right? Any question on this? Okay. All right, so the next block, let's just do the next block, and then we can adjourn. The next block is the filter plus load resistor. This is what happens if I have, so the following up, right? Following up on here, as you can see, from Vx, it goes into filter. All right, so what is the transfer function of this filter? We already did this transfer function, right? Now, what about the filter transfer function? So right here, I redraw the circuit diagram right there. So the input is Vx, the output is our filter. And this filter, it doesn't have ESR. If that's the case, I can just do, that's the output voltage. I can do voltage divider, right? So I won't go through the derivation. If you do voltage division, then you get this right here. That's the transfer function, okay? For the filter, V out over DS is equal to Vs over the whole thing right here, right? So it starts from V out over Vx first, right? Because the input to that block is Vx, right? And this is the low pass filter, and this is the output, right? So V out over Vx is equal to, and we know that Vx by itself, as we already learned, is D times Vs. So right there is the voltage divider, and at the end I get the ratio of V out over duty cycle. Okay, almost done. If you have ESR right there, then you can still do voltage divider, except now the equation changes, right? That's the ESR right here, right? So now we have a longer equation for the transfer function right there. However, in practice, the ESR is much less than the load resistor. If that is the case, then this transfer function reduces to that transfer function right there, right? This becomes just one, and what else? That's about it, right? So that becomes one, and you just got this reduced denominator, right? Notice one more before I let you go. If you don't have ESR, look at what happens. There is no zero. There's no finite zero, right? You see that? There's no finite zero. Once you add the ESR, look at what happened. On the numerator, you see a finite zero. See that? That's what ESR does for us, okay? Which is important next week when we talk about compensator. Right? Adding ESR affects our stability, right? Because ESR introduces a zero, finite zero, okay? That's all I want to go over for today.